So in the last video, I introduced four new functions to you in terms of what the parent functions look like. We looked at the cubic, in other words, x cubed. We looked at the square root function. We also look at the absolute function, and we also look at the reciprocal function, or 1 over x. So this lesson, we're going to start looking at yet another type of parent function, what we call exponential functions. But before we do that, let's do a quick review of what those four other functions look like. And the thing that I want to highlight in terms of a warm-up, and this is going to be really important for the rest of the unit, is that we went through a lot of points to take a look at what those parent functions look like. Here on fourth, because we know what a cubic, what a root, what an absolute, and what a reciprocal function looks like in general, we just need certain key points to sort of start the initial points on what that graph will look like. And we're going to use these points on our parent function over and over again throughout the rest of this unit. So this is why going through this is important. So here we have a table of values for f of x is x cubed. And really when we looked at the x cubed, the three really important x values for x, is 0, 1, and negative 1. So when we have f of negative 1, that's going to be negative 1 cubed. We're going to get negative 1, 0 cubed is 0, and 1 cubed is 1. So we plot that on our graph. And let's put it on a scale here. So 2, 4, 6, 2, 4, 6. The zeros. Okay. And maybe because it'll almost look at linear, maybe the best ones might be 2 and 8, and negative 2 and negative 8. So 2 and 8 would be up here, negative 2 and negative 8 would be down here. So here is what the cubic looks like. Again, a little bit like the yin-yang or curve to it. So the next one is the square root. Again, we're going to come up with some key x coordinates for the square root that we want to sort of initially graph with. So it's going to be 0, 1, and 4. So here, square root is 0, 0, square root of 1 is 1, and square root of 4 is 2. So again, we do a quick plot. And there's 0, 0, 1, 1, and 4, 2. And again, the square root function looks like a shooting arrow. That's a little bit too high. Let me flatten out a little bit. And so that's what it's going to look like there, the shooting arrow. The next one is the absolute value. So here, the key points on our absolute value. And notice I'm writing f of x and not y, because we sort of really need to get used to that notation in this unit from unit 1. And that really talk about functions in general. And notice that every single time we've defined f of x to be a certain function. In this case, it's the absolute function. And the key points here, maybe we'll use the same as the cubic, negative 2, 0, and 2. So the absolute value of negative 2 would be 2. The absolute value of 0 is 0. And the absolute value of 2 is 2. And let's label our graph. So we get 0, 0, 2, 2, and negative 2, 2. And we know that the absolute value is going to be two straight lines in the formation of a V. So that's what that one looks like. And the last but not least, the most trickiest one of them all is the reciprocal function. So in this one, we're actually going to have 6 key points for x and x, because remember, for the absolute function, there were sort of 2 parts to the graph. So that's what we need to set 3 points for each part to give us a look. So whenever I graph the absolute, the reciprocal function, I always want to put in the asymptotes. Oops, that's a little bit too thick. Make that a little bit smaller. I also want to always put in the asymptotes, because it's going to help me draw those curves. Because remember, with the reciprocal function, our curves are going to get closer and closer to our asymptotes, but never touch it. So in our parent function, the asymptotes were x equals 0, in other words, right here, and y is equal to 0, in other words, right here, the x-axis. So the key points for the x, we're going to start off with 1, 2, and then we'll go maybe to a half in the other way. So f of a half is 2, f of 1 is 1, and the reciprocal of 2 is just going to be 1 over 2. Likewise, we're going to do the same values for negative. So here we're going to negative 1, negative 2, and negative a half. So f of negative a half is going to be negative 2. F of negative 1 is just negative 1. And the reciprocal of negative 2 is going to be negative a half. And we're going to quickly kind of plot this. So 2, 4, 6, 2, 4, 6. And so we get to 1 comma 1. So that's really one of the main key points of the reciprocal function, is that I don't call it the center or the middle of that curve, but it's where, well, I'll just say 1 comma 1 is the key point on there. Then we got 2 and a half, will be right there, and then a half and 2 will be right there. So it's really kind of tight because of the scale, but I'm going to carefully draw these lines so that's going to be closer to that asymptote but not touch it. So it looks like that. And also on the other side we have negative 1 and negative 1, negative 2 and negative a half, and negative a half and negative 2. So again, carefully draw the asymptotes, and this is why I guess I said that negative 1, here's the other kind of key point, because when I sort of start drawing it, I draw from that point, and then carefully draw my asymptotes. So not draw my asymptotes, draw my lines close to the asymptotes. And so it's going to look something like that. All right, so there's a quick review on how to draw those 4 parent functions. And now let's look at exponential functions. So for this unit, for those other 4 functions, we're not going to really deal with word problems. Unlike quadratics, where actually it's very relevant to real life situations, those other ones aren't so much. But with exponential functions, we do actually discover that exponential functions do model a lot of things that happen in everyday life. So when we get to financial stuff, it models such as compound interest, population growth, resource consumption, and in chemistry and science, something like half-life of radioactive materials. I would also say that in our time of COVID-19, exponential functions are very prominent in today's discussion around the math of how much the virus is being spread amongst our population. But we're going to probably take the opportunity to explore these real-life applications later on in the year when we look at sequences and series, where this idea of exponential functions or the use of exponential functions come back. So a couple examples of exponential functions are y is equal to 3 to the power of x and y is equal to 1/4 to the power of x. So in general, exponential functions are of the form y is equal to a times b to the power of x. Okay, so really the definition of exponential function comes from the fact that our variable x now is not in our base, but it's actually in the actual exponent now. So that's where the variable is. So going back to y equals a times b to the power of x, we have the coefficient a, and later we're going to discover that when we talk about transformations, just like we did with quadratics, this is really the kind of vertical stretch and compression part of the exponential function. And then finally we have the exponent x, and x can be any real number, and that's what we sort of looked at Unit 2 when we talk about rational exponents, and recognize that exponent could be not just an integer, but any rational number as well. So here it could be any real number, in fact, so rational or irrational numbers. And finally, b, or base, is going to be a positive constant, but it can't be 1. Okay, in fact, we'll be very specific in that b must be greater than 0 and less than 1. So it could be between 0 and 1, or it could be just strictly greater than 1. So we're going to discover that's what the only values of b that we're actually interested in. So these functions are very different than the ones that other ones we looked at, for example, y equals x squared for in terms of quadratic, or even the cubic, y is equal to x cubed, or even something like y is equal to 1 over x. Okay, each of these functions, other functions, x is in our base. We can think of everything as a power. Everything has a base and exponent. You might think, well, this one over here doesn't have an exponent. Well, it does. It has an implied exponent 1. But in this case, x is in our base. So the difference here, again, exponential functions is x, our variable is actually in our exponent. So what does that graph look like? Well, as I kind of mentioned before, if we have no idea what a graph might look like for a particular function, we always could use the table of values. Remember, a line is now not a line. When we graph it, it's not a line, but it's an infinite set of points. How do we get those points? Is we take certain values of x, and then we get resulting values of y, and then we plot them, and then we plot enough of them, in fact, an infinite amount of them, we get the idea, we get the exact shape of that graph that represents our equation. So here, let me label the graph, x and y. And let me put a scale in, so 2, 4, 6, 2, 4, 6. And I kind of said that I always like to start with 0. Because 0 is, you can think of it as the nice middle ground, special properties around 0. And we discovered that actually most of these functions, the only exception is reciprocal, is that 0 is actually a very key point in terms of where our apparent function looks like. So in this case, what's f of 0? So in this case, our function here, I cannot emphasize this enough, is that f of x is defining a function. In this case, we define it to be 2 to the power of x. So f of 0 is really 2 to the power of 0. Well, anything to the power of 0 is 1. We're going to start incrementing x, or going x by 1. Let's look at f of 1. Well, that's just going to be 2 to the power of 1, which is going to be 2. When x is 2, so what is f of 2? That's going to be 2 squared, which is 4. And maybe we'll look at 3. And here f of 3 is going to be 2 to the power of 3, which is 8. Now, conversely, we want to look at going negatives. Can x be negative? In other words, can we have a negative exponent? Well, absolutely. That's what I think we discovered last year in grade 10. But we'll review it here again. So f of negative 1 is really 2 to the power of negative 1. But what does a negative exponent mean again? It really means that we flip our base, or we reciprocate our base. The idea of the reciprocal function is coming back. So we reciprocate our base, so the base is 2. Well, 2 is a fraction, it's 2 over 1. So we reciprocate 2 over 1, we get 1/2 to the power of 1, which is 1/2. Then we look at negative 2. So f of negative 2 is going to be 2 to the power of negative 2, which is really 1/2 to the power squared, which is 1/4. And lastly, we maybe look at x equals negative 3. So f of negative 3 is going to be 2 to the power of negative 3, which is 1/2 to the power of 3, which is 1 over 8. Okay, so this is why we really is important that we understood the reciprocal function in order when we look at the exponential function, we make use of that. Because when we reciprocate our base, and our base is an integer, it becomes 1 over that base. So how does that graph look like? Well, we're going to graph 0, 1. And maybe I'll do this in a different color so it comes out a little bit better. So 0, 1 would be right there. And then we got 1, 2 would be right there. And then 2, 8 shoots up right away. Okay? So that's one thing we discovered about exponential functions. Compared to any other function, it grows the fastest. Okay? In other words, as x gets bigger, the y value or resulting value grows or gets much bigger faster than any other function that we sort of done. Even x cubed, x to the 4th. In fact, it doesn't matter what the exponent is, x to the 100. We're going to discover that exponential functions grow a lot faster. Let's plot the other way. Where x is negative 1, so that's going to be 1/2. When x is negative 2, that's going to be 1/4. And you can kind of see that it's going to be harder to plot anything really after a half. Do my best for a negative 3, sorry, negative 2 was a negative a half, negative 3 is a negative, so positive 1/8. And so this is going to be a smooth curve. I'm going to draw from left to right because we're going to discover that, yes, with an exponential function, we have another asymptote. So here is another asymptote for the exponential function, and here that's going to be y is equal to 0. Notice it has another horizontal asymptote, and that this curve is going to get closer and closer to 0 on the left, but it will never reach it. And if your understanding of y, the reciprocal function 1 over x, as x gets bigger, it will get closer and closer to 0, but it will never touch it. And that's what's happening over here, because when we reciprocate our base, we're always going to get 1 in the numerator. The denominator gets huge, much, much bigger, but again, we'll never get to 0. So it is sort of like, dare I say, almost like the opposite of this, in that it's just going the other way to the left for the exponential function. So let's look at the characteristics. So the domain of this is, well, x can be anything. In other words, we could have any value for our exponent, especially some people say, well, no, we can't have 0. Remember, anything to the power of 0 is 1. What's the range? So the range here is a little bit tricky because YER, but in the case, what's the values of y? Notice that we're always going to get a positive answer. Question is, can we get an answer of 0? And we sort of highlight this already. That's why the asymptote exists for an exponential function. It will get closer and closer and closer to the answer of 0, but it will never reach it. Can never have an answer of 0. So here the range is strictly greater than 0. The intercepts, well, here the y-intercept is just going to be 0, 1. So this point over here. And that kind of makes sense because anything to the power of 0 is 1, and we're not going to have an x-intercept because, again, we're never going to get the answer 0. The asymptote, so there's going to be one asymptote. It's going to be a horizontal asymptote. In the equation, that horizontal line is always going to be y is equal to something. So in this case, y is equal to 0. So a couple other questions we want to answer over what interval domain is this function increasing? In other words, as x gets bigger, where is y getting bigger? And in this case, we will discover that's actually everywhere. And nowhere is it decreasing. In other words, nowhere is it where x is getting bigger, and we're actually going to get smaller values of y. Okay? And hopefully, if we see from the graph, it's really apparent that the exponential function is an increasing function. Well, let's explore some more things about this. So here, when we get consider y to the power of x, let's look at our table of values again. So this 2 to negative 2 is going to be 1/4. 2 to the power of negative 1 is going to be 1/2. It's going to be 1. 2 to the power of 1 is 2. 2 squared is 4. 2 cubed is 8. And 2 to the power of 4 is 16. So hopefully you kind of see a little bit of pattern of exponential function is that here, as we start from 0 going up, we're actually multiplying by 2. And notice that there's a direct correlation or connection between our base and what's being multiplied for each of our values going up. And that kind of makes sense because we're here, our base is 2 and our exponent is going up. That means we keep multiplying by our base, or in this case, keep multiplying by 2. Likewise, when we go in this direction up here, we're actually dividing by 2. Because again, we reciprocate our base when it's negative exponent, so we're actually dividing by our base every single time. So what we want to do is look at the first differences. So first difference, so here 1/2 minus 1/4, that's going to be 1/4. 1 minus 1/2, that's going to be a half. 2 minus 1, that's going to be a 1. 4 minus 2 is going to be a 2. 8 minus 4 is going to be 4. 16 minus 8 is going to be an 8. So hopefully if you see a pattern is that we're actually seeing the same numbers again, right? So here we get 1/4, a half, 1, 2, 4, 8. So let's do a second difference. And because we're getting the same numbers, the second differences are all going to be the same as well. So 1/2 minus a quarter is going to be a quarter. 1 minus 1/2 is going to be a half. 2 minus 1 is going to be a 1. 4, sorry, I missed 1. 4 minus 2 is going to be a 2. And 8 minus 4 is going to be a 4. So where most other functions, where our exponent is not x, the first differences will, what we say, merge. In other words, it will come to a certain point where the first differences are all the same. What we discover with the exponential function is the first, second, third differences, if we keep going on and on, we're going to get these same numbers. So they never merge. So that's one important thing that we're going to see with an exponential function. And again, what we're going to also note is that even as we go from the first differences from each value, each of these are being doubled or multiplied by 2 as well. So we have this idea with our base being 2 is that when we go from one y value to the next, as x increases by 1, we're actually multiplying it by that base. Okay? So the last thing we want to look at, I think the last thing, oh no, not quite, but the last thing in terms of graphing is that, well, we looked at a base of 2. Now we want to look at what happens when we have a base of 1/2. In other words, here, we looked at an explicit example where b was greater than 1. Now we're going to look at an example where a b is between 0 and 1. Okay, and what kind of pattern or what can we notice there? So again, we're going to start with 0. Start right in the middle. Well, f of 0, in this case, is 1/2 to the power of 0, which is remember, anything to the power of 0 is 1. When x is 1, so f of 1 is going to be 1/2 to the power of 1, which is just 1/2. And then what happens when x is 2? Well, we're going to get f of 2, which is 1/2 squared now, which is 1/4. And when x is 3, we're going to get f of 3, which is 1/2 to the power of 3, which is going to be 1/8. In other words, 2 to the power of 3 is 8. And what happens if when x becomes negative? So let's look at -1. F of -1 is just going to be 1/2 to the power of -1. So again, we're just going to reciprocate our base, which happens to be 2/1 to the power of 1, which is just 2. What happens if x is -2? Well, we'll get f to the -2, which means we got 1/2 to the power of -2. Remember, negative exponent means we reciprocate our base, which is now 2/1 squared, which is 4. So what we're seeing here is some very similar numbers to what we had above. Now on the -4, so jumping the gun a little bit. -3, so f of -3 is equal to 1/2 to the power of -3, which is going to be 2 to the power of 3, which is 8. So we sort of chose a base that has 1 as a numerator on purpose, because when we reciprocate that, 1 becomes a denominator. So we're going to have an integer that we're raising this to a power. And here we actually got the same values that we get with 2 to the power of x. And that should make sense, because what's the reciprocal of 2? Reciprocal of 2 is a half. And what's the reciprocal of a half? It's a 2. That's why we're getting the same values here, because when we have the negative exponent, we're reciprocating the base. So let's plot this, and let's see what the graph looks like. Is it going to look the same as y to the power of x, 2 to the power of x? Well, let's take a look. So we still got 0, 1. So again, I'll do this in red. We still got 0, 1, but notice as x gets bigger now, our values are getting smaller. So when x is 1, we get a half. When x is 2, we get a quarter. And this is where it gets difficult now, because when x is 3, we get 1/8. Really tough to plot, but we get the idea. We're at -1. When x is -1, we get a value of 2. When x is -2, we get the value of 4. When x is -3, we get the value of 8. So it's sort of like it's a mirror image of what we had before, because really the values kind of jump the y-axis a little bit. We still have our asymptote, and that we're going to get closer and closer to 0, but again, we're never going to touch it because we can never get the answer of 0. So let's connect this with a smooth curve. So I'm actually going to go the other way again, from left to right. And knowing that I have an asymptote here, draw that line getting closer and closer to the x-axis, but never touch it. Okay? So here we're going to discover the domain. The domain is also all real numbers because, again, our exponent can be any real number. The range in this case is also the same as the other one. In other words, we're only going to get answers that are positive and we cannot get 0. The intercept is the same. So y-intercept, again, y, because anything to the power of 0 is 1. So we're going to discover the y-intercept for every single exponential function. The base, the parent, is going to be 0, 1. And likewise, the x-intercept, that's going to be none, since we could never get the answer. In our asymptote, we still have one horizontal asymptote of y is equal to 0. So in this case, this function is actually decreasing. Hopefully we could see that as x gets bigger, our y values are getting smaller. So we can see that from the actual computation as we're doing. As x gets bigger, our fraction gets smaller. And likewise, we can also see from the graph, and I'll do that in a different color. We can tell from the graph that as x gets bigger, this line gets closer and closer to 0, and it's getting smaller. All right? So the last example we want to do is, now that we're given a graph, how do we determine the equation of this? So as I said above, all exponential functions for now will have the form f of x is equal to a times b to the power of x. So that's one thing I'm just going to stop here and highlight, is that a big difference between the exponential function and all the other functions that we looked at in the previous video, so the cubic, the reciprocal, the root, the square root function, and the absolute, is that there's only one parent function. But the thing with the exponential function is that for every single base that we have, each of them is a different parent function. So here we have f of x to 2 to the power of x. That would be a parent function. F of x could be 3 to the power of x. That is a separate parent function. F of x could be 1/3 to the power of x. Again, that's going to be a separate parent function. So every different values of b, that's a different parent function. Notice that for the parent function there, a is always 1. So it's just f of x is equal to b to the power of x. So in this here, how do we figure out what a and b are? Well, we could figure out what b is by giving our y values. So here we have incrementally increasing x by 1, 2, 3. And because we have that, here we can say that, well, how do we get from 2 to 6? We need to multiply by 3. How do we get to 6 to 18? We need to multiply by 3. How do we get 18 to 54? What happens if we multiply by 3? In other words, the ratio, and we're going to discover this later on, we'll talk about sequence and series, but the ratio here is the same. In other words, 6 divided by 2, 18 divided by 6, 54 divided by 18, that ratio is 3. This gives me my base. So here we can say that f of x is equal to a times 3 to the power of x. How do we get my a value? Well, we know that anything to the power of 0 is going to be 1. So 3 to the power of 0 is going to be 1. But when x is 0, my actual value here is actually 2. So how do I get from 1 to 2? Well, we need to multiply by 2. So that's how we get our a value here. So f of x is actually going to be 2 times 3 to the power of x. And notice that here we need to be careful. I have to indicate that we're multiplying, or else it's just going to look like 23 to the power of x. But here we have 2 times 3 to the power of x. And BADMAS tells us that we have to do 3 to the power of x first before we multiply by 2. So here's a summary that's, I think, taken from the textbook in terms of we're looking at exponential functions. And it's a big summary of everything we looked at. Really, we looked at these two graphs over here. When b is greater than 1, that's what the graph looks like. And when b is between 0 and 1, that's what that graph looks like. So that's all we want to focus on for this section. It's just those two aspects. Okay, and here is a little bit summary of everything else that we talked about in one short diagram.